Hi, my name is Messick, and I recently had the opportunity to work in Donald Sparks' lab, working on a project that focuses on how sea level rise affects nitrogen and phosphorus cycling in Delaware coastal sediments. So, as you can tell from the title, Delaware is susceptible to sea level rise, and this threatens systems by disrupting nutrient cycling within waterways. Sea level rise, when it does happen, can increase salinity or induce salinization. When this happens, it can have effects on biotic and abiotic constituents. So a biotic constituent would be microbes or plants, and an abiotic constituent would be mineral solubility. So changes in nutrient cycling with sea level rise can be caused by anthropogenic runoff of nitrogen or phosphorus, which results in harmful algal blooms. So this is bad because when you have an excess of nutrients in an ecosystem, it can cause death of fish or plants within the ecosystem, which obviously is not great for the ecosystem, so this should be avoided. Salinization may also change bioavailability of nutrients and thus the rate and extend these algal blooms or eutrophication zones. So for our project, we looked at 2 sites in Delaware Bay. One site was found closer to the bay and the other site was found further inland. So our site named 112 is for the sample collected closer to the bay, and our site called 113 is the sediment collected further inland. So we gathered these sediments, we extracted the aqueous medium from the sediments, and then we took our solid phase sediments and put them into reactors, and the reactors comprised 3 different water types. So we had a freshwater, a mixed water, and a seawater type medium. So then we used the different mediums and different time points to look at 2 different methods. So we used an Icp-Ms sampling method, and then we also used a UV-Vis sampling method. So with the Icp-Ms sampling, we looked at iron concentrations within these reactors and at different time points, and then using UV-Vis, we looked at ammonium concentrations within different time points of these 3 different types of waters. So going into the results, you can see from my results section on my poster that the initial characterization of the sites, you can see that 112, the site found closer to the bay, had a lot more phosphorus and a lot more ammonium within the sediment initially than the 112 sediments, and thus showing more salinity within the 112 site, which you would expect to see considering it's closer to the bay. So first I want to go into the UV-Vis data for the ammonia, and I want to look at site 112 initially first, which would be found closer to the bay, like I've said. And in this graph, you can see that there's initial decrease in ammonium in all of the conditions, and which is followed by a release into solution in the seawater and mixed water. So ammonium in the freshwater remains removed from the solution. That's just an initial overview of that first graph. So going into the ammonium for site 113, you would see a removal of ammonium from solution at day 3, observed for the seawater sample, and which is also similar in the 112 data. So next I want to look into the iron concentrations. So the iron concentration, there's a clear production of aqueous iron occurring in all 3 matrices in the first 5 days, with the highest production in the mixed water sample, and aqueous iron decreases in all 3 matrices after the first week in the 112 data. So then moving to the 113 data, we see that the aqueous iron production occurs in the first 5 days, with the highest amount produced in the mixed water, as we would see in the 112 site, and there's no aqueous iron production was observed in the freshwater system. which is interesting to see. So to wrap this all up and have a little discussion and conclusion, the aqueous phosphorus, which is not shown on my poster, did not change throughout the experiment, which is good to note considering that couples with salinity and what we're looking at. The mixed water matrices led to the most aqueous iron production and removal and release of ammonium. The intermediate salinization and the water mixing may lead to interesting and dynamic geochemistry. More work needs to be done to fully understand how this will affect biotic and abiotic processes influencing geochemistry during salinization. So really just more work needs to be done to fully understand these processes and why these minerals and such as phosphorus and iron and ammonium are doing what they do in the water systems. So to conclude my poster, I would like to acknowledge the National Science Foundation for funding this project in the state of Delaware and the EPSCoR grant. Thank you for all that you've done. And I also would like to thank Dr. Donald Sparks for giving me the opportunity to work in his lab. And I would like to thank Beth for all of her help on this project. Thank you for your time, and I hope you enjoy the rest of your day.